to know what happens to its angular velocity. So if we have a spring and it's stretched, so the first spring there on the left, that's the spring just as natural length, much like, suspiciously, these springs resting here. All right. And now we're going to hang a mass on it. And it's going to stretch it some extra distance d. Okay? And let's see. Then what we're going to do is we're going to stretch this guy and let go. All right? And we want to find what is the angular velocity of that guy. So this one, let's use forces for this one to set it up. Okay. So let's start with the one on the left there. So at equilibrium. Okay, so if we draw the mass, this is equilibrium is what I'm calling when I have the spring and I just hung the mass on it, but I'm just letting it sit there, not moving. So we have gravity pulling down. Let's see. The spring is pulling up. How much is the spring stretch? It looks like I stretched the distance d at equilibrium. And I'm going to call my downward direction positive. Okay, so if I do my sum of the forces in the positive downward direction, let's call that direction x. Okay, the sum of the forces in the x direction, I'm going to get mx double dot always, right? So if I do those, I'm going to end up with mg minus k d equals, what is x double dot in equilibrium? 0, because it's another way of saying it's not accelerating. Okay, so it's equal to 0. Therefore, I can say that mg equals kd. This might come in handy a little later, so I'm going to box it. Okay. So now, I'm going to pull this guy at distance x. And I want to also draw some of the forces on this guy. So I'm going to call this stretched. Okay, so now, very similar free body diagram. I have mg, except for now pulling up on it, the spring is stretched a total distance x, right? So if I do my sum of the forces in the x direction, and again, I'm calling down as the positive x direction. So let's see, I have mg minus kx equals mx double dot. All right, well, I'm thinking I might be able to make this a little prettier if I change my variables around a little bit. So you notice that in that distance x, if I define a new distance, which is how much did I actually pull it back? So we put this guy at equilibrium. This is your distance d. Let me define a new distance y to be how much more I pull it from that position. Okay? The reason I'm doing that will be clear in a second. So you can see from this diagram that the total stretch of the spring equals d plus y, right? So if I take the derivative of that expression, what's the derivative of d? 0, it's just a constant, right? So if I take the derivative again, I'm going to get x double dot equals y double dot. I'm going to make that substitution here into my equation. And I'm going to end up with, so let's see, I have x equals d plus y, and I have x double dot equals y double dot. Okay. Let me come over here and sub those in. All right. So let's see. I have mg minus k x. Now instead I'm going to write d plus y. And instead of x double dot, I'm going to write y double dot because they're the same thing, right? Okay, so now if I simplify that out, I'm just going to expand out the k. Okay, what do you notice about these first two terms? Yeah, we just said before that mg equals kg, right? So if I plug that in here, they're equal and opposite, so that's going to go away. All right, this is looking pretty nice. So I have minus ky equals my double dot. All right, let's bring everything over and divide by m. So it looks like I'm going to end up with y double dot plus k over my equals 0. Therefore, my omega squared, say omega, is k over m. This is the exact same thing we got for the horizontal spring that had no gravity acting on it. So you can see that gravity has no effect on its angular velocity. But now I want to ask, does this omega, oh, right here? Yes, sorry, there.
So we said that omega was angular frequency, but you call it angular velocity interchangeably. Is there a difference?
Oh, that's my mistake. I should be calling it angular frequency.
Okay.
Thank you for pointing that out.
Okay.
You're right. Thank you. Yes, angular frequency is the proper term. Angular velocity is for rotations. Thank you. Okay, so we have omega is the square root of k over m. We found it for horizontal spring. We're also finding it for a vertical spring. But I want to see does it actually make sense. So I'm going to need a volunteer. All right, come on up. I need you. This is a very difficult job. I need you to tell me which one is heavier. The bigger one is heavier? Okay, good. Awesome. Okay, so let's see. If I have a greater mass, so let's say I'm going to start with a small mass. All right. So maybe I have a timer. Actually, let's just do this. Let's look at the angular frequency. You tell me what qualitatively you see. All right. So get a good feel for how this thing is bouncing up and down. Now, if I increase the mass, what should happen to that frequency? Let's try again. This spring. Okay. Let's restart. Let's do the small spring first. Small mass first. Okay. Much better. All right. Let's try to get this going nice and vertically. All right, so we got a visual for what that angular frequency looks like. Okay. Now let's try with the bigger mass. Hopefully this won't. Ah. All right. Did it slow down? Yes. Okay, good. So that seems sensible. All right. I need one more volunteer. All right, Conrad. So you need to tell me which of these springs has a stiffer spring constant. As if you guys didn't know already. My previous demo. All right, so according to Rachel, she says that the green one is much stiffer. Do you guys believe her? Yes. See, I did it all. All right, so I'm going to pick the small mass. First, we're going to go for the red one has a smaller k, right? Okay, so let's look at its frequency. Okay, get an idea for this? Okay, now let's try with the stiffer spring. Okay, which one has a higher angular frequency? The green. Does that make sense? Let's see. It's in the numerator, so if k goes up, omega should go up. Sweet. So this equation seems perfectly sensible to me. All right. Hey. All right. So what? Okay. So on the front slide, on my opening slide, I had pictures of all sorts of systems that were oscillating. But so far, we've only talked about masses on springs. Masses on springs are awesome, but they're a very small subset of cases in real life. But what I want to tell you is that the tools that we've developed today are actually quite general. So if you have a very ugly looking potential energy function such as this, let's zoom in on that. See this potential well? That may be where something might get trapped. So let's just for a moment, let's shift our axes over there and pretend that we're zooming in right around that region. You can see if I superimpose a quadratic, something like, I don't know, 1/2 kx squared on top of it, you can see that right around the bottom of that well, it fits pretty darn well. Okay. Okay. So what that means is that near this minimum, near this little well right here, we can approximate this very ugly potential energy function as behaving like springs. And it actually turns out to be a rather good approximation for many very complicated physical systems that if you zoom in near a stable equilibrium point, if you're very close to it, it looks remarkably like a spring and it undergoes simple harmonic motion. All right, so I think everybody here either has been or is currently in physics 22? Yeah? All right, remember the pendulum where if you take, pendulum. So if we had the amplitude really big, was it independent of angle? No, we were kind of somewhere outside of this nice region. This is not the energy for a pendulum. Don't think that it is. But we were not necessarily close to this stable equilibrium point. But what happened if we did really, really small amplitudes? Yeah, it actually oscillated quite nicely, and it oscillated in simple harmonic motion. So pretty much any smooth destroying force functions, they look approximately like a spring near stable equilibrium, which means that they have a force that looks roughly like negative kx. Okay.